all of this compacted into, meaning these ideas, into something that that looks simpler. So consider the job of cooling a wafer of electronics. It's a disc-shaped thing, except it could be big, not only small. Think of a pizza, okay? And I don't like that because I should be able to draw better. And this thing has a thickness which is not important. I call it T. It generates heat uniformly, meaning heat arises if, like the rain, and on this thing, and heats it up. But the thing is cooled from the center. I won't get in details. It is cooled by a stream of coolant that flows perpendicular to the blackboard, because you're installing many of these disks on that stream. The point is that the rest of this disk gets hot, but to prevent it from melting, you equip it with high conductivity blades. Here's one, here's another, and here's another. You can make them radial, but equidistant. Equidistant. Let me make another one here. Okay, well, forget about the blades. What you've done is you've divided the disk into several sectors. And here is a sector. And I'll draw that sector here. In fact, let me draw it much bigger. And this sector has a size which is called area sub S, S from sector. And it has a length, horizontal, which is the radius of the disk. And it has a vertical dimension, which is measured along the perimeter of the disk, called H. But this H, in my version of the story, and by the way, it is only my version of the story because I'm the one who wrote this thing first, okay? I call it capital H. And next two things happen. First, I'm cheap. I'm not, splitting hairs. This sector looks like an isosceles triangle. So I'm at ease with such simplifications. And this means that the size of the sector, this AS, is H times R. This is a formula that will become useful several times in what happens next. Now, the reason I divided the disk into sectors is that whatever happens on the disk happens because of what happens in one sector, because you see, I wrote axis of symmetry here, but on the center line, I will put a high conductivity blade that I'll describe next, of a blade of thickness D. Anyway, the axes of symmetry are these, the edges of the sector. And that means symmetry in heat conduction means no heat transfer across a line or plane of symmetry. So in the sector, you have the old problem of carrying heat from the area to the point. meaning everything in the triangle is warmer than the point, the center of the disk, meaning T0 is the cold spot. Hey, Miles, put your head lower so that Jacob could see the triangle. Okay. Where are the hot spots in this triangle? In the corners. So this is one, and the other one is a mirror image. What is the current that arrives at the center? Well, it is the rate of heat generation. So the Q here is the volumetric heating times the volume of the pizza slice, which is A sub S times T. And this Q is driven by the temperature difference from corner to center. And so we're interested really in, so first of all, this T max minus T0 over Q. To make it smaller is the object of the game. To make it smaller at fixed Q means to make it cooler. Usually it's the other way around. The colleagues in electrical engineering will tell you what this maximum allowable temperature is so that the circuits don't start melting. So at fixed temperature difference, to make this thing lower is to cram more electronics per unit volume. All of this is good, no matter how you look at it. And as you'll see very soon, you can do this by allowing this drawing to morph freely, meaning you give it degrees of freedom. We'll see how that works. First of all, this the numerator, this thing is called delta T, and it has two recognizable contributors. One is the temperature difference in the vertical direction, which I call, as I've done already, delta T Y. And then the temperature difference in the horizontal direction, or the radial direction, delta Tx. We went through this already in the previous lecture. We invoked the formula of Fourier twice. By the way, this delta Ty is between the temperature T max here and imagine the temperature called Tr at the corner. And, okay, Fourier. I just thought of him because he was a very modest person. Fourier was huge. He invented the Fourier series, which is a way of expressing as a series any function, any shape. And he was never able to publish his 10 or so papers about it. And boy, did he try on his meager salary as a fonctionnaire in Grenoble. He was the prefect of Grenoble. And but then he said, well, forget that. I'm going to publish it as a book. And he wrote this book, the analytical theory of heat. and became famous. So now he is at the French Academy, rubbing elbows with his detractors. One of whom was Lagrange. I told you about him. Where is he from? Italy, okay. And who spent most of his creative career in Berlin, with Euler. And his French was not very good. So Fourier wrote about Lagrange. Brilliant. Very bad speaker. Horrible French. So these are gems you have to dig deep for, because posterity does not engage in gossip. But I think it's quite interesting. Fourier. So Fourier, if you invoke him, then this. Let me draw the blade here, and landing on the blade vertically is a heat flux vertical. Now the heat flux vertical is the conductivity of this poor conductor called K0 times I write the order of magnitude, temperature difference scale, which is delta Ty, divided by the distance scale, which is h. So that's one formula to get out of invoking Fourier, which is the definition of conductivity. The other is the heat flux. By the way, before I continue, so this heat flux coming down, it comes down by sweeping downward all this Q triple prime collected over a distance h. So all this, let's call it stick of Q triple prime, multiplied by the height of the stick, makes the heat flux shown here. Okay, so what I just drew means that Q triple prime, the heat flux is Q triple prime times H, meaning something to substitute here a little bit later. You make the same move, well, let me not hurry. You end up with the estimate that delta Ty is of the order of H squared over K0, and then Q triple prime. I may have skipped one or two steps, but that's what you get. You make the same moves in the horizontal direction. You're talking about the blade of thickness D. So that's thickness D. Temperature difference is delta Tx. And then proceeding to the right is the heat flux in the x direction. So this heat flux in the x direction, which I should collect from here, is Kp, and then delta Tx. And then integrating this heat flux over the cross-section of the blade, you get the actual heat current that reaches the center, namely Q is Q double prime X, and then D times T. And by the way, this Q, I wrote it very early, is over here. In fact, let me just do that. So all these formulas massaged together lead to a second expression, which is for delta Tx over Q, and then R, and then Kp dt, where you know what Q is. this Q triple prime and like that. And you also know, by the way, this D, just like in the previous lecture, D over H is the volumetric volume fraction occupied by expensive material. And there will also be this, soon enough, you'll see K tilde, which is K sub P over K0. The next step is to get here and add these two discoveries. And so you have delta T of the order of, and I write them the way I have them, meaning H squared over K0 Q triple prime plus this other one, which is, let me write the Q triple prime AST. That was for Q, and then R, and then KP DT. You make the obvious substitutions, namely phi H here, over here AS is HR, and then finally you, in fact, let me write one more version of it, which is the first term does not change. The second one becomes a Q triple prime R squared over KP phi. And then this is the overall delta T. And then you non-dimensionalize this so-called delta T as a thermal resistance this way, delta T over Q triple prime A sub S, which would be the total Q per unit length, and then slash K0. So when you do that, you get, again, skipping one or two steps, H over R, because you see this AS is the product of H times R, and when you divide by it, you end up with here with H over R, and then plus 1 over K phi R over H. These things happen the way we've seen more than once before, the so-called mud wrestling between Roman 1 and Roman 2. By the way, this is what was happening during the Roman Empire. They were entertaining themselves. They had fights. You heard about the gladiators. That was murderous stuff. They had wrestling going on in the public square that was covered for the purpose with sand. Yeah. How do you say sand in Spanish? Spanish, help. Sand. The sand in the public square. By the way, because Italy was for centuries a province of Spain. This was in the second millennium. You don't know? Arena. Yes, arena. You go back to the Cameron arena, it says, hey, where's the sand? There's no sand on the floor, you know. Arena. It means that. It comes from those days when the wrestling in the sand, okay? So, obviously, the drawing you've seen before, there are two contributions. If you put H over R here, and one is this, the other one is the other way. I made this drawing many times. This time, the so-called best aspect ratio, H over R, happens at the HR that corresponds to the intersection of the asymptotes. And that's how you get the formula for how to make the design. So, results, or what you do with all this. Why use this? And well, first of all, you know the recommended shape of the sector, which is 1 over square root of k tilde phi. This is a formula you've seen before. And also the minimal size of this resistance. That will be useful as well. The exact, no, forget about, the exact formula actually is if all of this is called the resistance of the sector, then that resistance with minimal value takes the shape, meaning the result for delta T minimum over Q triple prime A over sector divided by K0 takes the exact, this is the exact answers are in the book. 2 over square root of 3 K tilde and phi. Where, by the way, this factor of 2 over square root of 3 is very close to 1. Because square root of 3 is 1.73, so we're not splitting hairs, so we can neglect these things. Okay, why is this useful? So you know the shape of the slice of the pizza. Well, immediately should be able to calculate the number of slices that fit on the disk. And that is the perimeter divided by the this face here, which is 2 times h. Which takes you to pi times r over h, which means pi over 2, and then square root of, that is, if you use the exact result for r over h, k phi. So depending on the product of these two dimensionless groups, the ratio of conductivities, and then the volumetric fraction of the highly conducting material, you'll have more or fewer of these slices fitting on the disk. Okay, remember that this group, you don't know whether it will be much bigger than 1 or over 1. In fact, there's a calculation here. You will have slices if n is bigger than 1. So if you force this group to be bigger than 1, you arrive at the criterion, meaning the product k phi having to be greater than 1, which means using the exact solution, K phi must be greater than 0.14. So if you're, they call it a bimaterial, two components is this way, then you have access to this kind of design rationale. There's another answer which I'll put here. Along with the number of slices, you predict the size of the disk. Meaning the area pi r squared, that turns out to be pi over 2 and then square root of 3k tilde phi times the size of the sector. So if you contemplate designs with the same size of the sector, the reason I'm assuming this sector of being of fixed size is that the sector in a drawing such as this is the smallest feature in the design. It is the elemental system. It is the fundamental. If you know the slice, you know the pizza. Get it? So for the argument shown here is about disks consisting of sectors of the same size. And depending on this factor, if this factor is big, then you'll have a bigger disk capable of accommodating more of these elements. So, in conclusion, starting with the sector or the pizza slice, you have the shape of the sector and the number of slices, which is related to the size of the entire disk. Get it? On that note, I hope all of you will be here next time we